Okay, in this long video, I'm going to finish this chapter. Um, More specifically, I'm going to finish section 4.5. It's about flocking or entity-to-entity interaction. So flocking um, refers to the behavior of many birds when they are flying together. Okay. Um, if a bunch of birds they're flying together, we say there is a flock. There is a flock of birds, and when they're flying together, there is also behavior called flocking, which means that these birds they are generally flying along the same direction. Although sometimes they could change their direction minorly, slightly, but in general they are flying along a main direction. And during this flying process, all those birds, they do not get close to each other too much to make sure that they do not collide with each other. They do not run into each other. Simultaneously, they do not fly too far away from each other, which means that the size of the flock won't be too big to make sure that they are safe in bad weather. They are safe when they're facing predators. So that's called flocking. And in this process, the interesting feature of it is that there is no something called hive mind or a leader or a set of rules set for the system. There is only a set of rules set for individuals, which means for each bird. Each bird is simply following this simple rules, this simple set of rules. They are loyal to this simple rules of individuals. But eventually, when we're looking at this system, at this flock, and consider this flock as a system, we can observe some behaviors that cannot be directly led by the simple individual rules. This is called emergence or emergent behavior. Okay, this is an interesting part about this system. And this flocking system is a complex adaptive system. So there are different types of complex adaptive systems in real world. Okay, I will introduce the concept here. So why do we call it complex? Because when we observe the system, the behavior of the system, these behaviors, they're not simple aggregations of individual events. Like I mentioned, all those birds, each individual is following a simple set of rules. And according to this rule, some behavior should not happen when we're observing this system, but they are happening. Okay, which means that these interesting behaviors you did not expect, they're only happening at system level, not individual level. Okay, we call this system a complex system, and also adaptive, individual and collective behavior. Collective behavior equals emergent behavior or emergence. They mutate and self-organize corresponding to the change initiating micro event or collection of events. So self-organizing or self-organized equals adaptive, which means that each individual is following a set of rules. And if there is change at micro level, some accidents or something surprising, these individuals, they will adapt accordingly. This is called self-organizing because nobody is telling it to do anything, to organize it, to redesign the route, but they will change, they will adapt according to that set of rules. Some examples here, right? Termites. Here is a net, or a hive of termites. Each termite is just a small ant. It's a small ant. And they are following simple rules. And together, they can build this relatively complex system and live within. Okay, traffic flows. Each car here, each pedestrian here is following their own basic rules, being safe, and maybe choose a best route to get to your destination with shortest distance or shortest time, whatever it is. A flock of birds, they're trying um, to get to another place for winter, right? They also need to choose a way that is safe with less bad weather and also with a lot of food along the road and get to that place for winter safely. Each individual is following simple rules, but together, termites, they can use this hive to defend themselves from predators. And traffic flows, they can change according to the specific volume of traffic, right? If you have ever if you have ever driven a car, you know that you want to avoid high volume traffic. And if there is an accident in front of you, and you know that you want to avoid that, these behaviors, they are happening at individual level. But when we are observing this system at system level, I mean, when we're looking at this hive, when we're observing the traffic flow of the whole city, when we're observing this flock of birds, their behaviors are very interesting and surprisingly new and should not be the results or consequences of that simple set of rules followed by individuals. Okay, they are self-organized systems. And in this course, we'll focus on bird flocking behavior. Okay, and in 1987, Reynolds proposed a very simple model for the simulation of flocking. He used some virtual birds to address this process, boys. Rules for these boys are very simple. Firstly, there is repulsion, which means avoid collisions with neighbors, which means these birds, these boys, they should not get too close to each other. Alignment is about direction and speed. Match the speed and direction of neighbors, which means you should follow the group. Not too fast, not too slow, and you should predict, you should perceive the general direction of the group and follow that direction and follow that speed. And there is also attraction to make sure that all birds, all boys, they stay within range of neighbors. Don't get too far away. Okay, you need to keep up with the group. Okay, so here, neighbors, neighbors. These all rules. They are for behaviors at individual level, because neighbors, they are defined based on a specific individual, and these rules, they are all happening locally within the neighborhood. Okay, which means this set of rules, they are simple. They are not for the whole system. There is no leader, there is no special individual that does not follow these rules. All birds, they are following these rules. Okay, so one rule: at each time step, a given particle or driven with a constant absolute velocity assumes the average direction of motion of the particles in its neighborhood of radius r, with some random perturbation added. So this model 4.16 here addresses that an individual should have a constant velocity, and the direction of that individual, which is theta, after each step should be decided by the average direction of all neighbors currently, plus some random noise. If this noise is not huge, this formula makes sure that each individual is following the general direction of its neighbors, because each direction is the average direction of all neighbors, right? And we usually consider this noise very small. There is some randomness, but it will not affect the general direction of each individual, okay? And if the speed, we're talking about the value of the speed, not the direction of the not the direction, okay? If the speed is a fraction of the neighborhood range R, and we set R equals 1, then this model has 3 free parameters. What is a free parameter? A free parameter in mathematics is a parameter that cannot be very accurately predicted. It can be estimated, but it will change constantly, which means there is always this dynamic there, okay? This parameter is not something constant. So here, speed is a free parameter, okay? It's always a fraction of R, but this fraction can be high, can be low, right? Density of individuals, density of birds, it changes when this flock is moving from one location to another. Sometimes it will be larger, sometimes it will be smaller. Maybe in bad weather, in a rain, these birds, they tend to get closer to each other to make sure that the influence from the wind, from the rain is minimized. If it is very good weather, they tend to get spreading out a little bit, right? And the range of random noise term delta theta is also a free parameter because it's random, which means that it will vary within a range. This range could be large, could be small, but it's also a free parameter. So this is a dynamic system. The speed and the direction of each individual, they can be addressed by this formula and these 3 free parameters. That's a very basic flocking model. It's only about the direction of a bird and also the speed of the bird. Okay. And let's talk about more complex factors in a flocking system. First one, neighbor. How to define neighborhoods. Okay, so here we cannot simply use Van Neumann neighborhood or Moore neighborhood, because that's the definitions of neighborhoods on a lattice. But now it's different. Right? For example, we can use a simple proximity, a square or a circle, to define the neighborhood of a target. For example, this solid black bird here is the bird of interest, right? If we use circle to define the neighborhood, then these birds with bold black boundaries, they are neighbors. Neighbor 1, 2, 3, 4, 5, 6. If we use a larger square to define the neighborhood, besides these 6 neighbors, we have 7th neighbor, 8th neighbor, 9th neighbor, right? And other 1, 2, 3, 4. Other 4 birds, they are in very thin, they are with very thin black boundaries. They are outside this circle, they are outside this square. They are not considered neighbors of this bird of interest, right? Obviously, these definitions of neighborhood is more complex than simply Moore neighborhood or a Van Neumann neighborhood, right? We can use even more complex method to do this, to define neighborhood. For example, angular range with preferred distance criterion, right? Here we still have the bird of interest, and a colon in front of it with a specific range of angle is considered neighbor. The gray area, right? The gray area is the neighborhood of this bird. So bird A, B, 3, and Z, they are all considered neighbors of this bird of interest. But not neighbor, a bird X is outside of this gray area. Although it's within this range of angle, but it's just too far away from the center, from this bird of interest. It is excluded, it's not a neighbor of the bird of interest, which is this black one. And another bird behind this bird of interest is also included because it is not inside this cone with a specific angle in front of this bird of interest. Okay, or there are many more methods defined by users. Okay, you can also slice the pie into different small slices. Of course, you can arbitrarily decide which slice is considered the neighborhood of the bird of interest. Right, this is totally arbitrary. This is totally arbitrary. For example, you can use slices and distance to define neighbors. For example, I would say 1, 2, 3, 4, 5, 6. We have 6 slices, but only this slice of pie is excluded from the neighborhood. So which means the rest 1, 2, 3, 4, 5 slices, they are considered neighbors. But let's just stop a little bit. Beyond this definition of neighborhood based on slice, we also want to add distance as another factor to define neighborhood. So this dashed circle here, of course, you can say that, okay, I only accept birds within this dashed circle as neighbors. If that's the case, then only this specific bird is on this slice and also within this dashed circle. But here we say that bird 1, 2, 3, they are all neighbors. And for some reason, this bird is excluded. But again, it's arbitrary. You can use different methods to decide the definition of neighborhood, right? And these details on the definition of neighborhood affect the flocking behavior, because like I said, all these rules, all these simple rules, repulsion, alignment, attraction, and also this simple mathematical formula to address the direction and the speed of the bird, they are all based on the definition of neighborhood. If you change the definition of neighborhood, of course, the behavior of the bird of interest here will also change accordingly. Because by the different definitions here, it has different neighbors. And it has different numbers of neighbors. Okay, so the definition of neighborhood is crucial to a flocking model. And we can also add something called body force into this model to make it even more real. Okay, a force acting between two individuals. Body force is a force acting between individuals attracted to one another when they are further apart than the preferred distance. Of course, you have to set a preferred distance first, right? If the distance between individuals is longer than this threshold, than this preferred distance, they should attract each other, which means they should get closer. But if it is the other case, some birds, they're getting too closer, the distance between them is shorter than the preferred distance, then there should be something called repulsion. This force here, repulsion here, should just push all those birds away from each other. So you can say, unless this is a perfect system, without any change, all those birds, they are flying on a specific, very accurate direction without any noise, and the speed is perfectly a constant, then they will keep this preferred distance forever during this flocking process. But as long as there is randomness, it's not possible to keep this preferred distance for a long time. So this body force is making sure that, or you can say this body force is addressing the fact that there is always randomness in flocking behavior. And flocking itself is always a dynamic process. There is always adjustment of directions and speed. Okay, of course you have to set a preferred distance and the relative body force, influence of preferred distance among flock mates relative to previous directional tendency. So which means that this body force can be very strong, can be relatively weak. Okay, and here is an example from the model library of the textbook. Again, I will leave it to you. You can play with it a little bit, and there are different parameters you can assign, you can set, and each red arrow here is considered an individual in a flocking behavior, in a flocking system, and you will say it's a very interesting system. Okay. And attraction, repulsion, alignment models of collective behavior. So obviously this is beyond flocking. Okay, it can be used, this model, this abstraction of real world system, attraction, repulsion, alignment system, it can be used to address movements of a lot of things, pedestrians, birds, of course, maybe a school of fish, maybe just some animals, they are living together in nature, right? Again, the system itself, attraction, repulsion, alignment model or system, is a building block model. Okay, you can give it a specific context, give it a specific meaning, so it can be applied in different realms, areas, right? There are three major factors, each with its own spatial expression. Attraction, to make sure that individuals are not too far away from each other. Repulsion, makes sure that individuals are not too close to each other. Alignment makes sure that individuals, they are moving along not exactly the same direction, but in general the same direction. Okay, applications include flocking, herding, right, schooling of fish, crowd dynamics. Okay, and some new interdisciplinary fields of focusing on mobile phenomena, right? No matter what kind of movement, right? They are about what? They're about mobile phenomena. Okay, so GIS science for moving objects, right? It can employ this attraction, repulsion, alignment model, data structures, indexing, queries, error analysis, and other examples here. As long as you can consider, as long as you can add the concept of agent or individual to your applications, and in your applications, these agents or these individuals, they move following a set of rules, then you can simply use this model here. Okay, flocking model, or you can say to be more universal or more general, repulsion, attraction, alignment model. Okay, and I've pasted a lot of literature in Carmen about different applications of the framework, of the random walk framework of and other models we have discussed in this chapter. Okay, animal movement, human mobility, and pedestrians and evacuations. Okay, you will say that, okay, as long as you are creative enough, these models, they have very meaningful, important, and crucial applications in our real world to make our life more convenient and safer and safer, okay? And yes, yeah, here is a summary of the content of chapter 4, RWs and mobility situation. At the very beginning, we talked about lattice random walks with 4 directions, then random walks with any direction you want, not only 4 cardinal directions. And we can also change the step length, not only the direction of the walk, but also step length. And we can make our walk steps more correlated to each other. But you should know that this correlation only exists locally. Remember the aggregation of small steps. When this correlated walk is long enough, the correlation, this correlated walks, this phenomenon phase, okay? And levy flies very meaningful to the foraging behavior of animals. It's also a very good model of our real life. A lot of small steps and some very rare but long steps. Okay, this random walks models, they are very simple, often used as null models, which means when you're trying to explore a new phenomenon, okay, you can use these models as what? As baseline, Okay, I was, for example, I'm observing a movement or something, and it looks like it looks like following levy flights, which means that I observed that this entity is moving with small steps usually, and suddenly it becomes paranoid or whatever you say. It jumps, it leaps a big distance, and then repeat the small steps. Obviously, it is following levy flights, right? So you can use this model and try to use this model to address the movement of this entity you're interested in. So that's the reason why these basic models, they can be considered as null models. Okay, then we discussed more complex walks or movement, foraging and searching behavior. It means that these walkers, they are not simply walking, they are walking with a purpose. They're trying to find food resources, right? And then we add even more to foraging and searching behavior. We add even more intense interaction between foragers and the landscape. More specifically, the resources can respawn, can regrow. And also, once a location has been visited by the forager, it cannot regrow resources for a specific time, which means which you can use to address the influence of forager on a specific location, right? There is damage after the forager. There is damage to this location, so it doesn't have the ability to regrow for a specific time. When it recovers, new resources can be found here, right? In our real world, it's very common. We log a lot of trees every day, and after that, we can consider this specific part of the forest has been damaged. It's not possible to grow trees immediately maybe in decades, right? In these decades, we can consider this location has been flagged as visited by human beings, right? So yeah, as long as you're being creative, you can just apply these models to different applications. Okay, at the end, we talked a little bit about flocking, not too complex, only very basic components for simulating flocking system or self-organizing systems. Okay, so there is emergence and complexity from interaction. So emergence or emergent behaviors, they are something you cannot predict from that simple set of rules followed by individuals. But actually, when you are asking these individuals to follow these rules, to behave, to live, to go, then something new, something you did not expect may appear, and that is emergent behavior. That's like the magic of collective behaviors. Okay, if there is only one individual, it will be predictable. It follows the set of rules you just gave it. And if there is a bunch of individuals following the same set of rules you just said, this collection of individuals will give you some surprises. Okay, that's called emergence. Okay, thank you. This is the end of chapter 4. We still have one chapter to go, and I will see you in the next video. Thank you.